Welcome back to Be Spice. In this session, we'll continue with mastering alarms. In session 13, we'll focus on how to avoid repeating alarms. So, repeating alarm in the sense, we are going to talk about, why repeating alarms occur and the methodologies. The first methodology, engineering of signals to minimize noise, then filtering methodology, then transient suppression and deadband and debounce timer, counter, and finally the threshold settings. All these we are going to talk about for this, how to avoid repeating alarms. Let's get started. Avoid repeating alarms. As you know, friends, repeating alarms, occur when an alarm is activated and clears repeatedly over a period of time. So they are the most common form of nuisance alarm because the operator has to silence the alarm and to accept the alarm each time it occurs, isn't it? So they may cause the alarm list display to fill up with same alarm message and obscuring other messages, right? So the bottom line, the repeating alarms are nuisance to operators and should be avoided through design. Okay. Okay, so that's the point. Now, let's see why repeating alarms occur. Repeating alarms occur. Repeating alarms can be generated in several ways. For example, the noise on the process variable itself when it's near an alarm set point, right? Alarm setting. And the second is the real high frequency fluctuation on a process variable, real actual high frequency fluctuations on a process variable. Then of course repeated on of control loops. So these are the scenario, these guys, the alarms keeps on repeating. Okay. So that is the, what you call reason basically. Now we'll go into how we can get rid of this. One is the engineering of signals to minimize the noise. As you know, noise on analog process signal can cause issues with controllers and on graphic displays, and also, it results in spurious repeating nuisance alarms. Okay, so process measurement. So to add on further, process measurement should therefore be designed to be as clean as possible. So that is the way out, right? For example, this means locating instruments at points where the process flow is not turbulent, okay, and avoiding measurements which are the difference between two noisy signals. So we have to do this during the engineering stage, okay, right? So the bottom line is many problem can be avoided just by applying established good instrumentation practices. So that's the point. Engineering of signals to minimize noise. Then filtering. Okay. You know, modern instrumentation can be very responsive and can often follow the high frequency noise on process signal. Low pass filtering is frequently required to reduce noise from such signal. We would have studied during our college days, right? Low pass filter, right? Okay. So low pass filtering can maybe applied using digital algorithm within alarm processor itself. However, because of the aliasing effects, any noise above the digital signal input sampling frequency should be removed by analog filtering before digital filtering is attempted. Okay. So this can create a significant load on the BPCS, that is a control system. So this filtering can be achieved by either by choosing an instrument with an inbuilt adjustable low pass filter or by having a filter in alarm processor analog input cards. As simple as that. Okay. So what are all the recommended time constants? Okay. For example, flow, we can do it 2 and level 2 second, pressure 1 second and temperature 0 second. So this is the recommended time constant that we can do it, individually tuned for signals used in controllers actually. Okay. So that is about the filtering. Now we go into the transient suppression. You would have heard this, right? Transient suppression. For example, friends, some processes are known to transiently pass through an alarm state, isn't it? So, for example, during startup, the current drawn by an electric motor may transiently reach levels well above the steady state high current limit, isn't it? So, Filtering based on the process running signal may be used to briefly suppress such expected transient alarms. For example, 3 seconds of the, following the starting of the pump so that you can get it off. So this is one such methodology. Okay, then the famous one, deadband. Okay, so you may be knowing this deadband, right? See, deadband is nothing but, it's a hysteresis, right? It's a range around which the alarm threshold within which changes in the process variable do not trigger a new alarm. Basically, it helps to prevent chattering, frequent toggling of alarms. Maybe I'll just try to, try to explain with an example. Take a case of high temperature alarm set at 100 degree. Without deadband, if the temperature rises to 101 degree, alarm triggers. If it drops to 99.9, the alarm clears. So if it fluctuates around 100 degree, the alarms keeps toggling on and off. Okay, with deadband, like for example 2-degree deadband. Okay, so alarm triggers when the temperature rises above 100 degree. Alarm stays active until the temperature drops below 98. So here the deadband is like this. So there is no, frequent on and off, right? The fluctuation. So having said this, so what is the set? What we have to do it? See, for flow and level, we can keep it at 5%, and pressure 2% and temperature 1%. So this is one such sort of methodology, right? How to avoid repeating alarms. Then the another one, debounce timer. Since many repeating alarms are the one that are occurring frequently, one way of reducing the occurrence is to use a delay of timer to eliminate clear right signal pair from the alarms displayed to the operator. So this is the debounce timer. So what is the set point? We can set it here. For example, flow 15 seconds, level 60 seconds, pressure 15 seconds, temperature 60 seconds, and others 5 seconds. So this is the one of the thing we can focus. Then another aspect is on the counter. Basically, counters can be used to detect repeating alarms by counting the number of times the particular alarm repeats. So basically this is done by having an up and down counter which is incremented up to a maximum limit. That is a point. Every time the alarm is raised. Okay. So if the alarm is repeating, the counter eventually increment up above a repeating limit. Up to this point, all alarms displayed to the operator in a normal way. After the repeating limit is reached, the alarm is displayed to the operator as a standing, and all subsequent rising or clearing alarm is hidden from the operator. Okay, this is the point counter. Then finally we talk about the threshold setting. Okay, see, for example, friends, we need to ask a lot of questions basically. This checklist can be used to support the process of setting an alarm threshold. What are all the questions? What is a normal value of alarm process variable? Very, very important. And what is the value at which financial loss, hazard, and environment damage will occur? Does there need to be a more than one alarm, meaning high and high? Does the alarm setting need to change according to operating condition? If so, why and when? Does the alarm need to be a combination of time and extend over the limit? Like for example, the overheating of motor due to high current? Yes. And how much does the alarm process variable fluctuate in normal operation? How much does it fluctuate in process disturbances which do not bring the alarm process item into a hazardous state? What deadband would be suitable? Is debounce likely to be required to prevent multiple repeating nuisance alarm? If yes, what would be a suitable time delay? So that's all I have for this, you know, topic, friends. Okay. So yeah, thanks for watching and keep watching, friends. I'll come out with the next, video with alarm shelving. That is also very, very important. Take care. Thank you. Bye bye.